Okay, so here this question says we have a solid mass gaining energy at a constant rate. So these are all clues in the question. Until it reaches its liquid phase. Okay, so it's going to change state. And it says the specific heat capacity, that's C from my formula, in the solid phase is greater than in the liquid phase. So CS is greater than CL. Okay, so then I look at this question, I see I have 4 graphs of temperature versus time, and I'm supposed to use that to figure out which one shows the correct variation in temperature of the mass with time. Now the only real clues that have been given in the question are that the specific heat capacity is greater in the solid phase, but the other big clue that I'm given is that it's heated at a constant rate. So this is a system again where energy is being added by something and it's happening at a constant rate. So when we talk about the rate of energy transfer, in other words, Q being energy divided by time, that's the rate of energy transfer, that is equal to P. Okay, so quite a lot of these questions involve this, relationship between power and Q and T. And so Q is equal to P times T. All right, and now I have a way to relate this to my specific heat capacity formula. My graph has time in it, so I needed some way to get time into the question, into the equation. So since Q is equal to MC delta T, I can now say, well, therefore P times T is equal to MC delta T. And now I want to relate this to my graph. But the problem here is that this time is on the x-axis, and right over here now I have it in my equation on the y side. In order to equate this equation to the graph, I want to get it in the form y is equal to mx. Now m here is the gradient. Don't confuse that with m, the mass. In fact, I'll change this and I'll call that big M so I don't confuse them. Okay, so how do I get this in the form y is equal to mx so that temperature is on the y and time is on the x? So I need to rearrange this equation right here. So since temperature is on the y, I'm going to move that over to the left hand side. So I could have mc delta T is equal to P times T, and I did that just by swapping the two sides. And now, since I want delta T to be on its own on the y-axis, I'll call that delta T is therefore equal to P times T divided by M times C. And now I have it in the form that I want it. If I just change it a little bit, delta T is equal to P over MC times T. And now it's in the form y is equal to mx, where y is delta T, and that's correct. X is the time, T, and that's correct. And therefore, what is the gradient of the graph going to tell me? It's going to tell me P divided by MC. Okay, so I'm going to go over here and write that. M, the gradient, is equal to P divided by big M, the mass, times C. But, P and M are both constants here. And that means that actually M has the gradient, has an inversely proportional relationship with C. So as the gradient increases, C decreases. And now I'm ready to answer the question, because it told me in the beginning that the specific heat capacity in the solid phase is greater. But C here is larger when the gradient is lower. So I'm looking for a graph that shows a lower gradient in the solid phase. Now I know that it has to heat up, then become a liquid, so it's going to change state, and then the liquid phase is going to increase in temperature. So I know that, in other words, this first phase is my solid phase and this second phase is my liquid phase. So I'm looking for one where the gradient is lower in the solid phase than in the liquid phase. meaning the specific heat capacity is greater in the solid phase than the liquid phase. And if I look, I can see that that is true for B. So here, the gradient is steeper in the liquid phase, not a lot, but it's the only one where the gradient is steeper in the liquid phase than the solid phase. I could rule these out straight away because they don't have any latent heat. We need this section here because this is the latent heat that is added while the substance is changing state. So I could rule them out straight away. And here, since the gradient here in A, in the liquid phase, is less than the gradient in the solid phase, that doesn't match up with what I want down here. Okay, so my correct answer is B.